Okay, so we're working on this problem. We're trying to look, we're going to see what's happening with addition in the complex plane, what's really happening in the picture. Our first vector, or first complex number, and it can be thought of as the same as 1 plus I. We figured out that the length of this vector is the square root of 2. We can write this in polar form as the square root of 2 times e to the I times e to the I times pi over 4. Now, this is our other complex number, 2i. This is in fact 0 plus 2i. The modulus of 2i is going to be 0 squared plus 2 squared square root. It's just going to be 2. So this r is equal to 2. What's the angle here? Well, clearly this is 90 degrees, or pi over 2. We can write this as 2 times e to the I pi over 2. Because this is going to mean 2 cosine pi over 2 plus I sine pi over 2. Cosine pi over 2 is 0. So this is 2 times I sine pi over 2 is 1. This is just 2i. What happens when we add them together? Well, we know by the way we add complex numbers. This is 1 plus 3i. And now let's figure out where that is. Maybe green. So 1 plus 3i is, here's 1, 3i is up here. I'll try and draw this nicely. So here is, as best I can draw, oh, jeez. Okay. Here is this. And that's, unfortunately, this really is a little less than perfectly straight. What I'd like you to see, if you can, if this was better drawing, and there will be better drawings in your book, this is called vector addition. This is vector v plus vector w. Incidentally, the little arrows are over there to show that they're vectors and not numbers, even though that these are just complex numbers. Once again, you'll start to get used to the notation, so don't worry about it so much. And I'm over teaching you as usual. This is down the road a little bit. This is called the parallelogram law. When you add vectors, you take the tail of the one you're adding. So we have this plus this. I'm going to remove this and stick it on the head of this. So this would be, usually do vectors with little pointy things like this. Here's the beginning, the tail, the 0 point. If I take this and put it up over here and add it together, I get this. So this, vectorially, what this looks like is this is our v, looks like an R. So here is v, vector v, here is vector w. V, and this vector here is v plus w. Okay, so this is what vector addition looks like in the complex plane and in other two-dimensional planes. Vectors are ubiquitous. They're the servant of physics and just about every kind of advanced science that I can think of at this time. So this is what this looks like. What about multiplication? Let's see what multiplication does, and let's see what we can figure out from what we know. What about if we square a number? And I'll have to get rid of this. This is actually not too bad of a drawing. If this was a little straighter, this would be good. Oh, similarly, maybe I should talk to you about subtraction. As a matter of fact, let me talk to you about subtraction as long as I'm right here. We'll use this same stuff. What if I take this vector v, which is a complex number, and now we subtract 2i? Suppose we do that. Then we're going to end up with 1 plus I minus 2i. This is 1 minus I. Okay, so now let's take a picture and put 1 minus I up. And let me get rid of this other junk so it doesn't confuse them. Okay, so here is 1 minus I. This is about as close as I can draw 1 minus I. And now here is this. What's the relationship between, what you'll notice when we did this, when we added vectors, so we took this vector, we added this to it, and we used the parallelogram law to take this out of the page, stick it up here, and then it just connects up to that. What about for subtraction? Well, for subtraction, what you do is you make this go the other way. So here I'm taking this, but instead of putting it up, I'm going to turn it down. And so this would be right here. And obviously the drawing isn't perfect, but this vector is now going to be v minus, I'll have to get rid of this, the vector w. So vector addition, you take the one that you're adding, you pull it off the page and place it up here using the parallelogram law. And for vector subtraction, you take it and you just turn the arrow around. Okay, so you can actually just do this numerically. You don't have to draw these pictures to get it. As a matter of fact, in real life, in real science, you don't want to be drawing pictures to figure out how far the airplane's going to fly on such and such fuel. I just wanted to give you a pictorial representation of what's going on. Now let's think about when we multiply vectors together and see what happens. And I'm saying vectors, in fact, we're not even at that section yet. We're just talking about the complex plane. But they're using this to introduce vectors, and they are, in some sense, they're the same thing. So remember from our formula here, we know that z is equal to r e to the I theta. What would, for any n, what is z to the n? What if I exponentiate this n times? Well, it must be this to the n. Remember, from your basic algebra rules, the n is going to multiply here and here, so this is r to the n, e I n theta. This is going to be r to the n cosine n theta plus I sine n theta. And this is a really remarkable result, and it's very handy. So, as long as we're here, let's do something else too. Let's figure out, suppose I have z equals, r e to the I theta, and then we'll let w equal, now what should I use? I'm going to use p, because I don't want to use the same r. These are going to be different. This is the modulus. Actually, you know what? I'll do it this way. I don't want to confuse people. We know that r, the radius, is the modulus of z. And so w is going to be the modulus of w times e to the I. Okay, so I'm going to call this theta 1 and theta 2. So a lot of times this notation is what drives people crazy. What is z times w? Well, this is going to be the absolute value of z, the modulus of z, and these are real numbers. These are coming out to the front, right? So this absolute value of w, e to the I theta 1 times e to the I theta 2. But remember, I'm sure everybody does, but remember, am times a to the n is a to the m plus n. So this is going to be the modulus of z times the modulus of w, e to the I theta 1 plus theta 2. So what happens is, when you multiply two complex numbers together, you're really multiplying their lengths and adding their angles. That's really neat. I have to flip over another reel of tape. We'll be back.